Okay, we are going to start talking about the normal distribution. Okay, here we go. All right, so let's see here. A normal distribution is bell-shaped and symmetrical. So a normal distribution, we're going to have this shape here. Nothing new. We have a mean in the middle. The probability is continuous, meaning basically it's uncountable. Okay, there can be all kinds of values for x. All right, the center of the bell shape is above the mean. Its shape is determined by the standard deviation. Okay, so normal curves can take on different values for the mean and standard deviation, but if we want to compare sets of data, then we need to do what's called standardize that bell curve. Okay, so we're going to look at a standard normal distribution. It's the same thing of what we're used to. The only difference is now we're going to let the mean always equal 0 and the standard deviation will always equal 1. So now for the bell curve, when we standardize it, okay, all sets of data will have a mean of 0 and our standard deviation that we add to the right and subtract to the left will have values 1, 2, and 3, negative 1, 2, and 3. When we standardize it, okay, we'll convert these values to something called a z-score. All right, so each data point, each x value will be converted to a z-score. The z-score will tell you how many standard deviations the x value is above or below the mean. Okay, if the z-score is negative, then the data point or that x value is below average or below the mean. All right, if the z-score is positive, then the data point or the x value is above average or the mean. Okay, there's a formula to find a z-score. So a z-score, we're going to take an x value, we're going to subtract the mean, and then we divide by our standard deviation. Okay, when we find a z-score, we want to use 2 decimal points every time. So we're going to need to make sure we round to 2 decimal points correctly when we're finding that z-score. Okay. All right, so here's an example of how the z-scores are going to work and why they're useful. Okay, we have a group of seniors who take the ACT. The mean score is a 22.3 with a standard deviation of 2.1. Okay, so here's the deal. What we're used to doing is putting the mean right here in the middle and adding 2.1. So we'd have like 24.4. I could add another 2.1, which is my standard deviation, get 26.5, and add. I could also subtract my standard deviation and have like 20.2, and I could keep going and have 18.1 and so on. Okay. Now what we're going to do when we standardize this, which we'll get to, is we'll say like 0, 1, 2, 3, and -1, -2, -3. Okay. All right. So this question says, if Derek scored a 25 on his ACT, how did he score? All right. So if I look, 25 might land, between 24.4 and 26.5, somewhere in here. So it looked like he scored above average. All right, so good job, Derek. All right, if Jessie scored an 18, all right, so here Jessie is 18. She's about right. Whoop, excuse me, right about here. Okay, so there's Jessie. So it looks like she scored below average. Okay, so if we keep going with this scenario here. All right, now when I do a standardized normal distribution, let me move these questions up. All right. What I would do is redraw this curve with the values of -3 to +3 right here. Okay, that's the only difference. All right. So what is Derek's z-score? So let's see, Derek had a 25 on the test. So for Derek, that means x equals 25. The mean was 22.3. And our standard deviation was 2.1. So for Derek, we're going to do z equals 25 minus the mean, and we're going to divide by the standard deviation. Okay. And we're going to get something and round to 2 decimal places. So when I subtract these numbers and divide by 2.1, I get 1.29. Okay, so now let's compare that to our picture. 1.29 should land let's see, this is where we had Derek, 1.29. So it looks like what we marked was pretty good because here's 1 and here's 2. So we needed 1.29 to land right in between 1 and 2 standard deviations away from the mean. Okay. All right, now let's look at Jessie. So Jessie had an 18 on her ACT. The mean is still 22.3. The standard deviation is still 2.1. So Jessie's z-score is -2.05, rounded to 2 decimal places. So let's see if that lines up to our picture. Okay, so -2.5, we had Jessie right here with the x value of 18. When we do the z-score of -2.05, that matches up. We need to be between -2 and -3, closer to -2 with that score of 18. Okay, so our z-score should line right on top of where our x values would be on the same picture. Okay, all right, so let's look at this example. We have 2 track teams submit their average times for running a 400-meter race. The Panthers have a mean time of 68.2 seconds with a standard deviation of 4. Kelsey is a runner for the Panthers, and her time was 70.5 seconds. The Raiders have a mean time of 67.8 seconds with a standard deviation of 5. Jessica is a runner for the Raiders, and her time was 70.01. Okay. So here's our question. If Jessica and Kelsey raced, who would win? All right, so Kelsey had a time of 70.5 seconds. Jessica had a time of 70.1 seconds. So Jessica would win the race. Okay. All right, what's Jessica's z-score? So for Jessica, we have a mean of 67.8, standard deviation of 5, and her time was 70.1. All right, so we have 70.1 minus 67.8 over 5. Z-score is 0.46. All right, for Kelsey, her team's mean was, let's see, 68.2, standard deviation of 4, and her time was 70.5. Z-score was 0.58. Okay, so let's think about this. All right. When we standardize this information and put it on z-scores, it doesn't matter that their teams had different means, because now we're looking at everyone has a mean of 0, standard deviation of 1, 2, and 3. So let's see, Jessica would land 0.46, like right here. Okay, and Kelsey is 0.58. Okay, so who is the faster runner compared to the rest of the team? Okay, so faster runners would be below average. Slower runners would be like over here above average, okay, because it's a race, so we want to be faster and below average. So since Jessica is closer to the faster spectrum here, she is the faster runner when we compare it to the rest of their team. Okay. All right. So next topic, the standard normal distribution. This is the area under a curve, and that is equal to a probability. The area under the standard distribution curve equals, this probability. We should have said 1 here. It equals 1. The total area equals 1, or 100% of our data. Okay. You can find the probability of something by finding the area under the curve. Okay. And we're talking about that bell curve. All right. So if I want to find the probability of an x value being less than or equal to something, okay, I would find the area to the left of that curve, and whatever that area is my probability. Okay, so we would find the area to the left. To find the probability of something greater than a given variable, we would find the area to the right. And on a bell curve, I would find like the area over here, okay? And to find the area under the curve, we're going to use this thing called a standard normal distribution table. And this table is going to list the areas. So I've got kind of a picture of a table here. In Moodle, you're going to be able to look at a printout of these tables. So this file is posted to you in Moodle, okay? And it's going to give you the area under the curve. So let's talk about this table for a second. Let's see here. So here's your z-score, all right? And if I want to look at a z-score of negative 3.34, okay? The first 2 decimals are given right here in this column. So I would find negative 3.3. Then the last decimal, the one in the 100th place, is given in this column. So I would have to find where there's a 4, okay, in that 100th space, and then I want to find where these 2 things overlap, okay? So the area to the left, if z was negative 3.34, is this little chunk right here. That area is 0.0004, okay? If I wanted to find the area to the left, if z was negative 1.65, I would go to negative 1.6 and find 0.05 and find where they overlap. And so the area to the left of this, negative 1.65, is 0.0475. Okay. On the second page, this is the first page where the z-scores are all negative. On the second page, our z-scores are positive. So here, if I wanted to find the area to the left of z equals 2.39, now I'm looking at 2.3 and going down to 9 and finding where these cross. And so the area to the left of 2.39 is a bigger area, so you find these probabilities are increasing, and I would get 0.9916. Okay, so that's how that table works, and you should print it out from Moodle so that you can have it handy when you're answering your questions. All right, so let me erase this. let's go back to these examples. Okay, and you can find different probabilities on Google if you don't like the table I posted. Just make sure the decimals match. Okay. All right, a few things. If the z-score is less than negative 3.49, assume the area to the left is 0 and the area to the right is 1. If you notice, the smallest z-score we have on our table is negative 3.49. Okay, so anything further to the left that keeps going this way, we're going to assume the area to the left is 0 and the area to the right would be 1. If the z-score is greater than 3.49, we're going to assume the area to the left is 1 and the area to the right is 0. So kind of the opposite thing. If your z-value is all the way over here, we're going to assume that area is true. Okay. All right, so we're just going to practice finding some areas here. All right, we're going to find the area to the left if z is negative 1. So for negative 1, we're at negative 1.00, so that area is 0.1587. We're going to find the area to the left as z is 1.24. So now I've got to go to my positive table. I'm at 1.24. Okay, so that area is 0.8925. Okay. All right, now we want to find the area to the right. Okay, so this is tricky. When that happens, we need to subtract 1 minus the area to the left. Okay, because this table is going to give us the area to the left. I need to find the area to the right. All right, well, the area from the left plus the area on the right will equal the total area, which is 1. So if I want to find that area to the right, I'll need to subtract the area from the left. All right, so the area to the right will equal 1 minus the area to the left, and this is the area on the table. All right, so for this next question, find the area to the right of z equals negative 2. All right, so I'm going to negative 2.00. Okay, so I need to do 1 minus 0.0228, and that will give me my answer of 0.9772. Okay, and that kind of makes sense to me when I think about that curve. Negative 2 is here, so the area on the table is 0.0228. The area to the right that I want looks like over half, which is 0.9772. All right. Find the area to the right of z equals 1.56. So I'm going to my positive table, 1.56. Down here, over here. So 0.9406. So I'm going to do 1 minus 0.9406, and that answer is 0.0594. Okay. All right. Now I need to find the area between two z-scores. Okay, so when we're doing that, let me draw us a picture. All right, I have 1.18 and negative 2.09. And I want to find this area between them. Okay, so let's find the area to the left of negative 2.09. All right, so negative 2.09. All right, so this area right here is 0.0183. And then the area to the left of 1.18, so 1.18 right here. All right, so this whole area is 0.8810. Okay, so to find just this area, what we're going to do is we're going to subtract. I'm going to subtract the 0.8810 minus 0.0183 for my final answer, which is 0.8627. Okay. All right, so similar question here. Find the area between 2.03 and negative 2.03. Not 2.03, 0.23, excuse me. All right, so let's find negative 0.23. Use this column right here. All right, so the area to the left here is 0.4090, okay? So that's this area. Now my answer is going to be the area in between these things. Okay, well, I'm going to notice something about this bell curve. This bell curve is symmetrical, and these z-scores are opposite of each other, which means that this area to the right is also 0.4090. So to find this answer, if I notice they're symmetrical, I can take 1 and subtract that area 2 times to subtract out these 2 parts, and it will leave me with that highlighted part in the middle, which is 0.1820. Okay. All right, next question, find the area to the right and the left. All right. So if I have an area to the right of 0.50 and to the left of negative 1.25, so that's this plus this. All right, so first I'm going to find the area to the left of negative 1.25. So here's negative 1.2. Let's find the 5 right here. All right, so this area is 0.1056. Okay. All right, then the area to the right of z equals 0.50. All right, so here we are, 0.50. Okay. So the area here is actually going to be 1 minus 0.6915. Which is 0.3085. And we're doing that 1 minus because we're finding the area to the right. All right, so I'm going to take this number, and I'm going to add them up. All right, so this answer is 0.4141. Okay, so I'm going to do the same thing for this next problem. Okay. All right, I need to find the area to the right of 1.33 and the left of negative 1.33. Ah, these z-scores are the same. Maybe I can use some symmetry here to help me out. All right, negative 1.33. Let's see. Oh, better get a different color. All right, negative 1.33 right here. Okay, so this area is 0.0918. All right, and these bell curves are symmetrical, so this area is also 0.0918. So I can just take that area and double it to get a total area of 0.1836 for my answer there. Okay, I'm going to pause this video here and make this 2 videos so it doesn't get too long.